Good morning, everyone. Thank you again for being here. I know this is a bit different from what we had yesterday, but I think we're gonna have very good presentations too. The first one is gonna be from Professor Álvaro Poveda, and he's gonna talk about damaged infrastructure in recent years in Costa Rica. The use of this microphone is because we are recording this, so it's a little weird, but just to let you know. Okay, so please.
Okay, good morning, everybody. I will try to go as quickly as possible because you have better things to do. And my presentation is trying to show especially pictures about our experience with the past earthquakes and how these earthquakes are related to the seismic code in Costa Rica. So that's what we'll try to do. In December of 1972, we have the Managua earthquake. Managua is the Nicaragua capital. It's outside of Costa Rica, but it's really close, as you can see, from our country. The magnitude of the earthquake was 6.5, depth 5 kilometers. The number of dead and injured people are approximations, really, but they are good guess. And it was terrible. In my personal experience, I lost a good friend in that earthquake. So it was shocking. At that time, I wasn't thinking in engineering or earthquake design or something like that, but that was something really close for us. Okay. More than 600 blocks in the center of the city were destroyed. The cathedral was several damaged and still is in the same way. I was in Managua about a year ago, and you can see the cracks and everything is exactly the same. The average building, the major buildings in that area were like this, no more than 10-story height. And for the ones that love baseball, Roberto Clemente died in that time in an airplane crash. He was bringing help to the people in Nicaragua. We have our own earthquake in Tilarán, April 1973. Magnitude 6.5, depth 29 kilometers, 23 persons dead. Cathedral was damaged, and the Tronadora is the small town right there. The Tronadora church collapsed, and it's right here. So you see, Managua is here, Tilarán was here. So it seems to me that at that moment, people feel that the earthquake were coming to San Jose. And we decided to do something. All pictures of what happened in Tilarán. Is a rural area, wood houses. There was a lot of mudslides, and the Tronadora church collapsed. And in answer to that, in 1974, we have our first seismic code. Okay? And it was really interesting. At that moment, the civil engineering school has a student finishing his master's degree in Berkeley. And the easy way to produce a seismic code was telling Jorge Gutierrez, his name, find everything that you can obtain in Berkeley and try to write something. And what is really nice is in less than 1 year, we have our first seismic code. It was really interesting. In 1986, we have the second one. It's a big change. Here you see the spectrum is a different for us because we have different ductility spectrum. Instead of using the R value that you guys use in the States, we have different spectra. And in 1991, we have the Limon earthquake. This code shows that the Limon province at that moment was really a low seismic zone. And Mother Nature tells us that we were wrong. So then we need to change our code in order to solve this problem. The magnitude was really large, 7.7. 48 persons in Costa Rica and 79 in Panama were dead. This line is the border between Costa Rica and Panama. And there was damage in about 80% of the national territory. And we need to rebuild about 500 miles of roads. A lot of bridge damage, infrastructure. You will see this tomorrow. Not the destruction, the road. It was not an easy way to learn about bridge design. And we have destruction in small buildings. Okay. 2002, we have the third code, and for first time we have commentaries of this. Is a complete new way to design. We introduce large changes in the masonry, concrete, and steel chapters of this code. And in 2009, we prove if that code was working or not. We have the Cinchona earthquake. This is a rural area with a small population, small buildings, but you see the depth. Only 5 kilometers was in the surface. It was terrible in that sense. 90% of destruction in houses, schools, churches, and buildings in the zone. And then we start learning. We have houses like this. You will see masonry house number 1, number 2, number 3. And in this case, there was partial collapse of some walls and total collapse of some areas of the house. Very poor behavior of the joints and the walls. And we start looking, what was wrong? The amount of walls that house have in each direction was okay. And so it was something really different. And we found these kind of things. The steel reinforcements inside of the masonry walls were completely rusted. And then we realized that the joints were not properly sealed. So when it rains, the water can get inside of the wall. And since these buildings are close to the volcano pass, and we have acid rain right there, the water gets inside and start corroding the steel reinforcement. So that explains why some walls collapse. It's not because they were not properly built, but The problem was the steel reinforcement was not properly placed, and there was no reinforcement when the moment of the earthquake hits the house. This is house number 2. And here we have another problem. There is no horizontal reinforcement in the wall. There is not a proper beam at the top. There is no connection between one wall and the other. And of course, we can expect this kind of behavior. This is a close look of that intersection. And you will find some vertical reinforcement really small. And that gives you problems. House number 3, partial collapse. There were people injured in this house, and very poor details of the connections and connection between the beam and the wall, and how the beam bear on these walls. Number 4, there was some pieces of the wall that was not connected to the control. And the quality of this steel reinforcement was something that get our attention, because you see the 4 steel rebars were broken. And it's not a good thing. Main road problems and soil failures in the entire area. Silo collapse. This guy used to buy this kind of silos in America, but they buy it by cost. They were not concerned about earthquake. I've researched this company, and they offer you low seismic silos, or medium or high. The cheapest are of course, the lowest. So what happened is that the owners of these farms buy the cheapest silo, and these were designed for corn or some kind of thing. And instead of that, they use melaza. That is a mix of honey and other things to feed the cattle. And the weight is completely different. And of course, we found about 12 of these silos with the same behavior. Tension anchor failure at the bottom, and cold form steel buckling on the brace frames. 2010, we have our 4 seismic code in the commentaries. This is still in use right now. We are working, and we are hopefully have a new code in 1 year. We will try to do that. And in September of 2012, we have the Samara earthquake, or Nicoya earthquake. It's in Guanacaste area, 7.6, 5.4 kilometers depth. And we have very large damage, especially in the main hospital that we have in Punta Arenas. That's what we have in that hospital. If I remember, it's about a 8-story building. And the building originally was a concrete frame. It was retrofitted with shear walls. And this is the compression failure at the bottom of one of these shear walls. The emergency stairs has these beams and have a lot of shear cracks failure. So everybody was afraid to use the emergency stairs. That's terrible. The main stairs, this guy didn't understand what is a proper design for shear. You see, it's unbelievable that a beam of this height in a hospital have this kind of cracks. Okay. The earthquake was early in the morning, about, if I remember, 7 in the morning. I was there about 3 p.m. It was a chaos. There was engineers from the municipal government. There was engineers from the professional college. There was engineers from the equivalent to FEMA here. There were people from the hospital. Everybody was there. And then I realized that I was the older guy right there. I tried to assign work for each one and get together. And it was difficult, but in about 2 hours after that, we need to meet with the medical staff and tell them you need to close the hospital. After that, I received a lot of pressure. People telling me that's wrong, that's not. At the end, I make the good decision. Finally, they need to throw out the building and start with a new one. And reinforced masonry walls in a hospital. And of course, if there is no reinforcement, you will see all the shear behavior. For a small country with a small economy, this is terrible for us. So it was tough. This is in Nicoya. Okay, let me tell you this. This is Guanacaste. The hospital is more or less here, in the orange spot. The rest of the buildings are going to be here in the peninsula. This is a 2-building store where the municipal work. And it's a good example of something that we are working right now is related to have some kind of a chapter in our code that take care of the design of non-building structures and other things like ceilings, glass, mechanical equipment. You see, this is what we call secondary damage. It's not a structural damage, but you cannot work after an earthquake with that kind of problem. Something really funny, a captive column with all the problems that you are supposed to, and it was in good shape. Well, this picture is taken in a stair. You are standing in a stair and you are taking the picture of the ceiling, okay? And all the cover get out and fall down. Broken these windows, and the most terrible thing, come down in the stairs. There was a lot of people working in the second story. There was 2 people injured, and both of them have the same problem. They broke their arms because when they were coming down, they were protecting their head with their arms, and all these things were falling down. And a lot of broken windows that come to the sidewall that is right here. This is another building in the same city, Nicoya Vice Building, and it's a rectangular shape here. But someone has a good idea and try to place these rooms right here in the corner. And you can see all these black pieces of plastic were there because all these glasses were broken and all the damage concentrate right here. I found the blueprints, and you see this is the corner. It's completely regular. So you see that when codes tell you that there is something about the regularity that you need to comply, they are right. All the problems concentrate right here. And the rest of the building was more or less okay. So this is the kind of thing that you need to pay attention to the recommendation of the code. Nicoya Hospital building, I call it hospital, but it's not a hospital. It's a 2-story, it's a small clinic built in the 50s without a code, with nothing, and very poor details of the steel reinforcement, and it's an anchorage failure of one of the beams, shear failure in columns. The space between the stirrups is really large. And outside of the building, we have another problems. It's a large liquid gas container. And the people of the hospital tell us that there was a strong sound in this area, that something happened right here. And this is a close view of the connection of the container with the saddle. It really moves. So you need to have something different here. You need to have a wider saddle, and this piece needs to come a little bit more higher. This is another building. It's more or less in good shape. You will see all the ambulance here. And you need to pay attention to this beam. They have this first story, and then they decide to make a second story right there. And in order to go from here to the second, they build this stair. And in order to accommodate the stair here, look what they do to the concrete beam. This is the stair, this is the concrete beam, and this is the reinforcement. They cut the beam right there. So you lose all the anchorage here. You see the reverse cut? So I'm not concerned. Well, at that moment, I wasn't concerned about the stair. I wasn't concerned about the ambulance. What happened if that beam fall down? That's Santa Cruz Court, just a building. This is a 4-story building, and in the last floor they have this concrete frame. This is a concrete beam, but this is a concrete gutter. And the connection of this frame with the rest of the building was only through the roof system, and the steel trusses are really slender and were not properly attached to these concrete beams. So from the beginning, all the ceiling come down, and you will see of these trusses were buckled. It means that this move in this direction perpendicular to the frame. The columns has a lot of flexural cracks here because they work in the final store like a cantilever. And this is a picture from the roof. And if you can appreciate how there is a separation here that you don't see here. So this moves in this direction about 4 inches, but really large. Inside of the building, we found something like this. And when you have a close look, you try to understand why there is some styrofoam here. Someone has a good idea, and what about the inspection? Who was in charge of the inspection? Mechanical equipment, we see a lot of this. And that's, for me, this is as important as the main structure. We need to pay attention to this kind of problems. Design of racks, design of ceilings. Santa Cruz Municipal Building, this original was a bank, and for some reasons finished like a municipal building. It's a very heavy structure, concrete structure. And this is the other side. If you pay attention, this is a large element with a beam here. And this is an envelope for the stairs. And you see here the column, the beam, and you pay attention here, that's what you find. So you need to pay attention how the structural elements work with the non-structural elements, how to make some kind of separation between one and the other. And inside, you will see something really nice. This was a building that was designed for an architect. And the engineer, in this case, didn't learn the word no. Sometimes you need to say no. This is a mezzanine, okay? What we call a mezzanine is a second floor, but that piece of second floor doesn't cover the entire area, so a partial area. So this concrete beam is supported in this wall, not in a proper way. You see the crack. In another places, there's a beam, there's another beam here. Something happened here. It's a vertical crack. And it's from here, but it doesn't follow the 45-degree. And it's because the load is not applied in the normal way. Finally, we realized that this is the mezzanine and was supported by this tension member to the roof. Terrible. It's an international sport. You see the crack. And finally, in 2013, we have our first seismic code related to bridges. That's my presentation, just really quickly, in order to show two major earthquakes and why there was another two that pushed the decision to start with our seismic codes. And we are still learning, as usual. I don't know if you have any question. Okay.
Thank you, Professor. Now we have the presentation from Professor Juan Caicedo from University of South Carolina. He's going to talk about uncertainty quantification in the damage identification of civil infrastructure.
Thank you very much. Oh, that's right. I need to use this. Okay. So first of all, thank you for inviting me to Costa Rica. It's been a really good visit so far. It's really a pleasure to see the similarities and the differences that we have in different countries and how that actually can help us build better infrastructure in the future. Okay, so I have a little talk here. We'll see how it goes. I understand that I am the only thing that is keeping you from a volcano, so I'll be trying to be quick. So what I want to do is talk a little bit about uncertainty quantification, because I think as we look at all the technologies that we're thinking about, this is an important part that I think we need to pay more attention. So let me start with some work that I did a while ago, model analysis. And if you're familiar with some of the early work on this back in the 2000s, we were looking at the way to characterize natural frequencies and mode shapes when we use ambient excitation. So let's say that you're working with a student, and you say, okay, just for you to start, go and collect some acceleration data and analyze the data and tell me what you find, okay? And then the student comes back and tells you, okay, well, this is what I found. The natural frequency is 3.2. What should be your first question? What units? Yeah, very good, right? What's wrong with that statement? There are no units, right? That is exactly right. That usually happens all the time, at least with me and my students. But so now when I go back and look at the work that I did back in the early 2000s, and I look at what we did, part of identifying the natural frequencies, mode shapes, and with that, trying to identify changes in stiffness, right? And when I look back on those slides, I find things like this. And I say, okay, well, you know, this is supposed to be different damage patterns for different floors. The shaded cells are where the damage is supposed to be, or the change in stiffness, I should say. The numbers are representing what my methodology came out with. Pretty happy back then. I'm not so happy right now. Why? What's missing? It's percentage, so I guess that's a unit, quote unquote, but what's missing? Yeah, that's exactly right. So if you look at this, the probability of a change of the stiffness to be 13.74, what is that? Does anyone know that? What is it? It is 0, right? Because you have that the change in stiffness is a continuous variable, right? It goes from 0 to infinity, or 0 to 100, I guess, in this case, right? It's a continuous variable. For a particular number, for a specific number, the probability of that number is actually 0, right? So not too happy with that at the moment. Okay, so let's see. So uncertainty is not quantified. That's the problem, right? And uncertainty is not quantified. So estimating uncertainty is definitely not easy. It is difficult. We have to learn new things, right? We have to learn new terminology. You start reading those papers that talk about uncertainty quantification. It's like reading something in Spanish or in Chinese, right? So why do we want to do that? We want to start going to all that trouble of estimating the uncertainty. Well, I think it can help answer some interesting questions. For example, how good are our results, right? Plenty of times we get a number with our numerical simulations, works beautiful. Then we take the data, we do the same analysis, we get the results, and we say, well, it worked numerically, it should be working now, right? That's how we treat many other things. But estimating the uncertainty will actually tell us whether or not, or at least give us an idea, it's not bulletproof, but it gives us an idea if our results are good or not. And we can start asking more interesting questions. For example, instead of saying, is there damage in this structure, I think something that is more meaningful for people or more meaningful for the owner of that structure is, okay, what is the probability of failure, right? So we're starting to communicate, I think, a little bit more clear with the owner of the structure, right? So help us answer those questions. Another question that we can ask is, okay, I have this particular bridge. I have a student A developing one model, a student B developing another model, a student C developing another model. All of the three of them are telling me different things. The data is telling me something different. What do I do, right? So it can help us determine what is the probability of a model, right? So it can help us determine which of those models is actually more probable. And it can also help us determine what is if you have different methods to do analysis of the data, you can actually determine which of those methods is more probable. So I think these are very interesting questions that we can start asking if we start looking at something about uncertainty estimation. All right, and here's the other thing. So So that's one thing. Okay, here's another thing. So do you guys recognize this picture? Probably seen it before. Yeah, where is this picture taken? Japan. Okay, e-defense. Shake table in the world, right? This is a full-scale building. You can see people around, really tiny compared to the specimen. And so really nice, we make these buildings, we test these buildings, shake them and all those things, and then we have how many points? How many experiments have we made? One, right? So, can we calculate probabilities with only one test? Oh, good. Hopefully by the end of the talk, you're gonna say yes. All right, let's do it. So, who can tell me what is the definition of probability? Okay, yeah, good start. Yeah. Okay, yes, that's correct. And let's keep going with that. Definition of probability.
Chances of some event to happen.
Perfect, right? It's the chances of an event happening, and that's absolutely correct. That's the frequencies. Yeah. I gave him a couple bucks this morning to say, but that's absolutely right? So that is the frequentist definition of probability. But guess what? There is actually a different definition of probability, okay? Which is a state of knowledge or belief. State of knowledge or belief, okay? And this is what I think we have a lot of opportunities to do things as engineers. So let me give you an example. Let me ask you another question, okay? Talk to someone next to you about what do you think the probability density function, you guys remember those, right? The bell curve and all of those things. Of the temperature in the North Pole today. Go, we'll give you a minute. Talk to someone next to you. How do you think that look like? X-axis is temperature, Y-axis is probability density. How does that look like?
What temperature scale?
What is it? What temperature scale? Doesn't matter. Fahrenheit, Celsius. Just you choose. Kelvin. Well, there you go. All right, let me give you 10, 9, 8. Okay, awesome. Remember, there's a volcano at the end of this talk, okay? All right, so, oh yeah, that's true. All right, so can someone say what you talk about? Well, how does that distribution look like?
It looks like a volcano.
Like a volcano, that's awesome, yeah.
But it's not infinite, because I don't think the temperature could ever be -1 billion.
Okay, perfect, okay, good. But you have perhaps a mean?
Yeah, maybe, I don't know what that is, but yeah.
What do you think?
Today at the North Pole,
Yeah.
-30 degrees Fahrenheit.
Negative 30 degrees Fahrenheit. And if I'm going to ask you, I'm going to push him to say, okay, you need to tell me a standard deviation.
Sure, so ±10 degrees.
Okay, absolutely great. That's excellent. So if with that information, you can actually calculate the probability that the temperature is higher than 40 degrees, right? Yeah. Okay, let me ask you the next question. How many data points have you collected? None, right?
Well, I mean, that's not entirely true.
Oh, so you've been in the North Pole. Yeah, that's exactly right. But you're expressing your belief in terms of a probability, right? And that is the opportunities that we have, is not everything has to be 100% data-driven. Great, if we have the data, let's use it, right? But as engineers, we have lots of experience, right? We, of course, I check the temperature in the North Pole every morning, right? No, I don't, but you get the idea, right? Okay. So when you think about Bayesian probability, the definition of probability is different. The basics of what it represents is different. It's the probability. Probability is a belief. What is your belief about something, okay? When you think about the one that we learn in school, it is completely different. It's a frequentist probability, which is the chances of an event occurring, right? And that has significantly, so, but because they're different, there are big changes on things as we understand them. So let's look, for example, about uncertainty. If you go back to your statistics class or probability class, you learn that the uncertainty can be classified and aleatory and epistemic, and this is when everyone starts sleeping, and you know what I mean? But anyway, but aleatory uncertainty is something that is inherent in the experiment. You know, you repeat an experiment 5 times, you're going to have something slightly different, so it's inherent, and it cannot be reduced, right? Epistemic uncertainty is because of lack of knowledge. So if you know a little bit better your experiment, you can measure a little bit more parameters, your uncertainty can be reduced, and that's the epistemic uncertainty, right? So if you follow the frequentist definition, this is true, okay? If you are a full-blown Bayesian person, guess what? This is gone. Aleatory uncertainty does not exist. Does not exist. Because look at our definition of probability. Is a state of knowledge. Everything is based on knowledge, so everything needs to be epistemic. Right? Everything is epistemic. There is not such a thing as an aleatory uncertainty. Think about this. The typical example of the coin toss, right? All right, so what is the probability of heads or tails? 50, right? If it hasn't been ingrained in our heads that is aleatory uncertainty. It cannot be reduced, right? How can I reduce it? Well, guess what? Now let's say that we have a way to measure the initial velocity of the coin, the initial angular velocity of the coin, to measure the coefficient of restitution of the surface where the coin is going to bounce, right? And we have a really good model of a coin. I bet you that we can improve our chances to knowing if it is heads or tails, right? So now we're saying if we are looking now at the definition of probability as the state of knowledge, everything become epistemic. Everything become epistemic. So that's one of the biggest differences that you see between the frequentist and the Bayesian thinking in terms of probability. There are other differences. I can talk for hours about this thing, right? For example, in the frequentist approach, a parameter has a true value, right? It is fixed, and data is random around that value. So for example, if you're measuring the natural frequency of a bridge, if you follow the frequentist approach, you're saying the natural frequency is a number, is a known, right? But it's fixed, it has a true value. And the data is some type of randomness around this thing, right? It, again, comes back to this aleatory involved in there. But the Bayesian is backwards, actually. The data is fixed. The data is what you just collected. You made a measurement, well, that's the measurement, right? It's a fixed quantity. As a Bayesian, you say, yeah, there is a true value, but I really what I'm worried about that value is not the true value, is my state of knowledge about that value. And because my state of knowledge is different, now we can represent this true value. Is not really a true value, it's actually a distribution, right? It's our belief about that particular thing. So very different. Again, that has great implications in how we understand the data. One of them is confidence intervals, okay? So do the same exercise. I'm going to give you 30 seconds this time. What is a confidence interval? Go. Talk to someone next to you. Confidence interval. Okay, volunteer, what is the confidence interval?
The probability that your estimate is within some bounds kind of thing.
Very nice, very nice. You guys are so predictable. So this is what Wikipedia University says. Okay, Wikipedia University says, well, a 95% confidence interval or a confidence level does not mean that for a given realized interval, there is a 95% probability that the population parameter lies within the interval. What that means is, it really does not mean, if you have a confidence interval that your frequency is between 1 and 2 hertz, that does not mean that the true value, there is a 95% probability that the value is in there. That is actually not the meaning of a confidence interval. What it means, really, is that if you repeat the process 100 times, right, that interval will be there 95% of the time. It's completely backwards as the way that we understand things as engineers, in my opinion. So let me ask a different question. Credible interval. Have you guys heard of this? This is the interval that now you have a 95% chance that your thing is in there, right? And you can arrive to a credible interval if you think about this as Bayesians, which it is about the state of knowledge. If you go back to the confidence interval, look at what's happening. We go back one more slide, or maybe two. We said, hey, this thing has a true value, right? The parameter has a true value, right? So we cannot say that the confidence interval is there is a 95% chance that the value is in there, because there is a true value, so either it is or not, right? If you think about probability as a state of knowledge, now you can actually say, hey, there is a 90% probability that is there, and that is the credible interval. Does that make sense? I know it's convoluted, but just trust me. The credible interval is what most people think as the confidence interval. Confidence interval is not really how we treat in most cases. By the way, there are several papers that actually talk about how scientists mix these two concepts, right? And that actually can have serious consequences in some cases. All right, so questions, we need to have questions, right? When you start looking at probability as state of knowledge, what you can do is you can now increase or better estimate your uncertainty with data, right? And you can do that through this equation. So what you see here is your theta is whatever parameter you're trying to determine, okay? Just think in your own field, whatever parameter you're trying to determine. D is your data, whatever data you're collecting about that particular system. And you can say that, so this over here is what's called the prior, and this is your original belief. This over here is called the likelihood, and it is the probability of the data that you collected given a particular set of parameters theta, okay? And what you end up with this process at the end is you have an updated value of your probability of your parameters. So now you have a probability of your parameters theta now informed by the data d at the end of the process, right? At the end of the process. Very important to realize, hey, this is a prior. It's a prior. It is always the belief of the person or the group of the people doing the analysis is embedded in the analysis, okay? So when you read a paper that is Bayesian, please understand that this is not all of that is data driven. There could be a little bit of bias depending on the experience of the person that is doing the analysis. I will argue that that is actually something good for us as engineers. Because as engineers, we actually collect all the experience through live by looking at damage and the earthquakes and all those things. And why are we throwing that information away? We should be using that experience that we have into our analysis, right? We have experience and we should be able to incorporate it in those prior distributions. By the way, you can do things that are a little bit more complicated just by playing with the same equation. You can do things like this. You can calculate probability ratios of models. So if you have model A, finite element this, model B, finite differences of the same phenomena. You can calculate the probability ratios between those two models. And that can help you choose which model to use for subsequent analysis, or that can actually help you choose both models, and you believe each model a certain amount, basically, right? All right, guys, so let me show you some applications. So this is something that we did several years ago at the University of South Carolina. And it is it's about fracture mechanics. So this is when you have a specimen. The specimen is loaded many times with some forces. Force, and you release the force. The picture is probably not super clear, but what this is what is called a compact test specimen. This will pull it this way. This pull it this way. And there is a notch in the middle. This notch is right there. There's a camera looking at the crack growth. And what you see is that as you start cycling this thing, the crack starts growing, right? It starts growing, it starts growing. The black sensors you see there, they're called acoustic emission sensors. They're represented by circles here in the diagram. And what they do is they collect very small vibrations in the material, very high frequency actually. And those are the ones that are released when the crack grows. So if the crack grows a little bit, that energy gets transferred through the material collected by the sensors. Okay? All right, so good stuff. And then when you look at this fracture mechanics, there is a law that is called Parry's law that is going to tell you, okay, the speed in which the crack grows is in this axis. And the stress intensity factor that is related to the changes in stress on the cycles, in each cycle, right, is somewhere in this axis, right? So as an engineer, what you want to see is you want to keep track of this crack growth, right? If your crack growth is somewhere around here, maybe you're not too worried. Even if you have a crack, it's a stable crack. You can predict where the crack is grow, how much it's going to grow in a year, things like that. Not to worry. Even in this space, right? This is what is called initiation. This is called stable crack growth, and this is where problems are, right? This is the unstable part of the crack growth. So as an engineer, what I really want to know is say, okay, where am I here, right? Where am I here? If I'm somewhere around here, maybe I can manage the problem. I can defer maintenance for a couple of years, and that's okay. All right, so one of the things that we found during this research is that there is kind of a connection between the amount of energy that these sensors are collecting and the crack growth. And I'm not going to go into details, but this, for example, shows the crack length in millimeters in this axis. This is the number of cycles, and this is the absolute energy that was collected by the sensors. And they kind of follow the same pattern, right? So we can actually create correlations between what the sensor is collecting and the crack length, right? And use that to develop a model. Then we develop a few models for the stress intensity factor where we say, well, let's just make something linear, why not? Or maybe with some exponential over here that we don't know what it is, or a polynomial, right? So we just come out, okay, let's just try these two things, these two models. U here is the crack length, I believe, and theta are unknown parameters for the stress intensity factor. Collected some data, put some priors on the thing, did the analysis, and come out at the other end is something like this. What you see here in the dotted line is the experimental data. In the x-axis is the number of cycles. In the y-axis is the stress intensity range. And what you see there is some lines that have the solid dot and the other one has the circle. Those are the two different models, right? And what we're showing here is the 95% high probability density. That's the credible interval. It's a fancy name for the credible interval, okay? And what you see is the number of cycles is small, the crack growth is stable, my model is telling me, yeah, look, this is your uncertainty, this is your uncertainty, this is your uncertainty, this is your uncertainty. You start getting into the unstable crack growth where the model cannot really capture that behavior and say, wait a second, something is happening. I cannot explain it, right? So instead of getting just one number, I get a distribution, and we can actually draw distributions from this. So I get a credible interval, and at the end I say, okay, something really bad is happening. I cannot trust the model anymore. I better go check the bridge, right? That's one of the advantages of using uncertainty in this type of analysis. Another example, this is something that was recently published, and the idea on this is the same idea of acoustic emission sensing. You see here is a really weird figure, difficult to understand, but I'll try to explain it. We have an x-axis, a y-axis, and a z-axis. You have some sensors, so it's a block of concrete. You have some sensors that are acoustic emission sensors, and then you have a source. The source, in half of what I'm going to show, was simulated, and the other half is created by what is called a pencil lead break. So you take a pencil, you break the lead on the specimen, and the acoustic emission sensors capture that energy. By the way, that is I think that is an ASTM standard. So there is actually, you actually have to use a specific type of lead. It has to be that long. They actually like sell the pens that is fancy stuff. So okay, good. So when you do this type of things, one of the important things on this type of analysis is to localize in the source. Where is the crack, right? Where is the crack? And the type of techniques that is used is by looking at the difference of the time of arrival of the signal, and then you triangulate with the crackers, right? Beautiful. It works great on earthquakes. Doesn't work that well in these little specimens. Why? Because sometimes it's not clear when the time arrives, right? Sometimes it's like, okay, which one is it? Which one of these peaks are, right? And there's people who have proposed different ways of doing this. Okay, so let me explain this graph. This one over here is the voltage of the acoustic emission sensor, right? And these over here are two different methods that are used to determine the time of arrival of the signal, right? This is an AIC picker. Basically what it says, you have some equations, and when you get to this low level, that's it. That's the time where we need to say this is the time of arrival. And there is another technique where you have some type of a standard deviation of the signal. This is the same signal, just amplified, so we can look at it a little bit better and say when you cross that threshold, that's it. Well, guess what? They're not in agreement, right? They're not in agreement. So what we can do is we can actually formulate a model that helps us decide whether or not one or the other one is correct, right? Create a Bernoulli random variable to say, is it method 0 or is it method 1, right? And then we can, with one single signal, we can start testing whether or not that hypothesis is correct for one or the other one. And we obtain is something like this. Method 0 is AIC. Method 1 is the threshold. And depending on, so this is for one particular simulated data. For sensor 1, it seems like the first method was better than the second one, right? Probability is high, a little bit higher probability. By the way, this is big numbers because it's just the number of trials in a simulation. So it's more like a histogram. But for other sensors, sensor 4, maybe because of the location where it is or something, I don't know exactly, the other method seems to be better. Huh, interesting, right? Well, good. It seems like it's telling us something. Let's see what else can it tell us. Well, it also tells us, if you look at this is the number of the sensor, this is what is called the onset time or the time of arrival of that wave. And you see the distributions on the left tell us the distribution of the time of the arrival of the method that was picked by the technique. And the one on the right is the method that was not selected by the technique. Interestingly enough, the ones that are not selected have higher uncertainty. Much flatter, right? Much flatter. So very, very interesting. And then we did the experimental data. We got very similar results to the ones that I showed for the numerical data. And when you look at the experimental data in terms of the location of the pencil lead break, if you only use the AIC picker, this is what you get. You get a distribution. It's still probabilistic, but you get a distribution that is this wide. The center is somewhere around here. If you do the floating threshold picker, This is your distribution, much more narrow, but is biased, right? You see, this is the true location of the pencil lead break, and this is the center of that distribution. And when you combine the two methods, right, and let the distribution tell you, the method tells you which one to select for each sensor, it's much better. It's actually not biased, and not as narrow as this, but it's at least not biased, right? Again, in this case, we were able to use this uncertainty estimation to guide us into what method to use for the data analysis. Anyway, I'm going to go through this relatively quickly. Let me just pass this. This is another example, much simpler example. We have two-story building. We're trying just to determine, okay, what's the mass of each building, of each floor, with only one sensor. If you do with only one sensor, you get the case where you have two areas of high probability density. Here in the x-axis is the mass of the first floor, and the y-axis is the mass of the second floor. So what do? We go back and look at the picture. Right? So which of these two pics do you think is a better explanation of the experiment? This one or that one? Based on this picture. First one, why? Yeah, they look about the same, right? Okay, now we include that information into our analysis, and then we get much better results, right? The point that I wanted to make with that little example is I also think that we're trusting methods too much, and if we just let methods run by themselves, might give us the wrong answer. If we try to combine the experience of people again with what the data and the methods are telling us, we might be able to do a little bit of a better job than we might be doing now. All right, so let me tell you about some opportunities in terms of these protective systems. I think one of the things that I've been thinking about is how can we use all this sensing and this actuation for different things. And one of the things that we've been doing for the last few years is use the structure as a sensor. This is a term that Hyung No from Carnegie Mellon is kind of coming up with. But the idea is we already have some sensors in the structure. Can we actually look at the vibrations of the floors, put some algorithms to this thing to determine some type of health status of that person, right? So there might be some opportunities for the same techniques, the same sensors that we're using to do something slightly different. Some of the applications, aplicaciones, I don't know, was late last night. It was half Spanish, half English, but anyway. That's right. I just wanted to share, right? It's just right. So some of the things that we're looking at is fall detection. So when you have elderly living independently at home, there are methods that we have developed to identify that the person has fallen. Detect changes in health. We're starting to look at gait parameters. I'm going to show a graph in a few minutes. Not a few minutes, like in 2 seconds. But when you start getting sick, your gait actually changes. So the question here is, can we use floor vibrations to determine those changes in gait? And there's some other applications, like for example, security systems as well, right, to complement current security systems. This over here is a little graph that shows an acceleration data. That was when you hit the floor. And one of the things that we can do is now we can back calculate the force that creates that acceleration signal. What you see in the dotted line is what was collected with an impact hammer. We have to validate it somehow, right? So that's with an impact hammer. And the rest of the lines are the ones that are calculated with the methodology. Notice that this does not have uncertainty yet, so I'm still not happy about it. We need to include uncertainty on this type of analysis. But it's encouraging because now what we can do is if we can measure the force of impact, we have a better idea whether or not the impact was created by me dropping the microphone at the end of my presentation or grandma falling down, right? So this type of technology hopefully will help us do that. Again, talking about more in Spanish. So one of the things that we're trying to do now is to prevent falls. And one of the things that is interesting is when you look at exercise scientists, they have identified that walking speed, for example, is an indication of your risk of many things. And somewhere around here, there is risk of falling, risk of dead hospitalization and fall. There you go. So if your walking speed is less than 0.7 meters per second, you are at risk of falling, believe it or not. So remember, walk fast. But it's interesting because I think we can actually measure the walking speed in a house with floor vibrations, right? It's plausible. This is an interesting plot. I have, so this is my house, by the way. So this is my house. This is when we had twins and they were 2 years old. So the house was a little kind of a mess. And what you see here is the day of the week, the hour of the day, right? And you know, you have to instrument your house, right? Because what else are you gonna do? So I put some sensors in the house, in the first floor. We collected data for several months. And the very interesting thing that we observe is, look at this. So my wife is like the smartest person I've known. She bought these like clocks that change color at 7 a.m. and they know that they cannot leave their, you know, their rooms until they can read, they can do whatever they want, but they cannot leave the room, right? Look, no activity, no activity, no activity, boom. Right, twins are downstairs, right, okay, now. Okay, nap time, no activity. Lunchtime, activity again. Nap time in the afternoon, right? More activity when they wake up after nap time, and then they go to sleep. So you can actually like measure people's behavior with this thing. So there's lots of opportunities on this type of technologies as well. Anyway, if you have any questions for later on, this is my email address, probably small, it's probably here a little bit bigger, but I'll be happy to answer any questions. Thank you.
So
We cannot hear you. You don't have the mic.
No, it's because of the recording.
okay. Stand here and not do this. So at this time, we're going to take probably, what time is it? So it's 11 o'clock. We'll do a half hour, I think, for the discussions. So similar to the discussions yesterday. We don't have slides to put up here, the questions. I think you remember some of the questions from yesterday. What I would ask is that we've had two really interesting talks this morning, and there's an interesting theme that goes with the uncertainty that kind of goes through, behind what the engineer thinks that this is going to get designed as and what it actually gets built as, and then uncertainty, in general, and how we can try to incorporate this in design. But if we can have some discussions, maybe based off of some of the things that we've heard about today, and questions or thoughts on some of the damage that we saw today as well, and more what the role of protective systems and maybe in retrofit or a new building, what sort of the role that protective systems might play in providing more resilience to our infrastructure. So, okay, so again, break into three groups. If it's the exact same three groups, shuffle it up a little bit, but a little bit different. And I think we can, maybe one group can stay in here, and let's see where else we can go. I think down by the restaurant, there should be some room as well. And then at 11:30, let's meet back in this room. Okay?